Okay, hello everyone and welcome back to your YouTube channel and welcome to this lovely video today. As you must be aware, we are working with this power system analysis software called IPSA. IPSA is a very user-friendly interface-based power system analysis software. And we are creating a series of videos related to implementing some classical test system in this software. And today is the part 2 of one series of video. Today we are implementing the FGL boss test system using this power source software IPSA. But before we start, I would like to say thank you to my colleagues and friends in IPSA and TNI. TNI is basically the consultancy company based in Manchester in the United Kingdom, and they are behind or collaborating with the development of this software that is called IPSA. Well, and before we start, I would like to remind you that every single presentation and slides, they are stored in my ResearchGate repository. As you can see here on the top, you can find the link and you can go directly over there and you can get the slides. Also, I highly suggest that you subscribe to ResearchGate because it's a very powerful social media for academics where you can find many scientific papers, publications, reports, and everything for free. Also, in this video today, we are creating the FGL boss test system, and this practical example will be uploaded into the GitHub repository together with many other files that they are available for you for free. And if you are watching this video, it's because you are in the YouTube channel. So I highly suggest that if you like the videos, please subscribe to the YouTube channel, activate the bell in order that you can receive notifications of the new videos. And also, if you want, leave a comment or a question. Also, I would like to invite you to subscribe to the social media, Twitter and LinkedIn, and you will be able to receive more information, more active information about what is happening on the research and development environment related to power systems. And finally, some of the users, they asked me to include an email address in the case that you want to contact. So here at the very end of this slide, you can see the email address. Feel free to drop an email. Well, time to start this video, and we will start the presentation related to implementing the FGL boss test system using IPSA. And this is the second part of this series of video related to IPSA, and is basically the practice. And the practice means that later in this video we are going into one computer and we will run IPSA and following the steps to create this FGL boss test system using the software. And the agenda, well, the agenda is very short. We will start with a very short motivation about the test system and specifically the FGL test system. I will show you the step-by-step implementation using the software IPSA for this beautiful FGL boss system. What we want to do is basically starting from the single line diagram and the data on paper. We want to finish here with a beautiful animation showing you the load flow or power flow of this test network. But what was the motivation of this test system? Well, between 2004, 2005, 2007, I was developing my own power system analysis software, including steady-state analysis and also dynamic. So At that time, I was developing the first part. It was related with the power flow, and I realized that there are many test systems available on the network, on internet. IEEE has some standardized test system. Also, SIGRE in Europe, they have many test systems. But something that I noticed is the lack of information of the intermediate calculations. For instance, if you are calculating a load flow, they will give you the whole set of data, the data set, and then you can get the result for the voltages and currents and powers and so on. But if you are a software developer, you would like to have numerical results, intermediate results on those calculations. For instance, you want to know the actual values of the admittance bus matrix, or you want to see the step-by-step solution of the load flow, for instance, the calculation for each iteration. So at that moment, I realized, let me start to create my own test systems. I will double check every single intermediate calculation, and I will be able to compare my numerical results, the numerical results of my software with those systems. Later in 2019 to 2020, probably is where we start to create more serious development, and we create the models of this FGL test system in DIgEnSysLab Power Factory, in Powerwall. That is another very interesting software that you can get for free. There is a demonstration version, an educational version that you can get, and it's very useful. And most recently, in this collaboration with IPSA, we have the possibility of using the software to create the FGL test system. All those test systems will be available at the GitHub repository. You will be able to download them from there, okay? Well, but the job today is implementing one of those FGL test systems, specifically the FGL3 bus test system using the software IPSA. And you must remember from the previous video. In the previous video, I described the topology. This is a ring topology at the transmission level. This is 115 kV transmission system. They are not a step-up transformer. The generators are directly connected to bus bar number 1 and number 3. And there is a lump load, constant power load, 400 megawatt, 200 MVA, connected to the bus bar number 2. What is interesting and very useful for my students and also everyone watching this video is the generator 3. The generator 3 is operating in what we call the PV mode. Constant power, constant voltage. And that means that this generator will deliver 200 megawatts at a bus voltage that this generator will try to control the voltage in a magnitude of 1.04 per unit. And I say try because in this case, this generator has reactive power limits. So the capacity of this generator to keep constant this voltage to 1.040 depends on the ability of this generator to fulfill those limits of reactive power. And I am saying this right now because in the video you will realize that when we run the load flow, the generator 3 will go to 40 MVR, and that means that it's reaching the maximum reactive power, and the voltage will drop from this. Because in real power system, when the generator reaches the maximum reactive power, well, we lose the possibility of controlling the voltage, the bus bar voltage, and in those cases, the generator change from PP operation mode to PQ. Well, if you go to the ResearchGate repository, there is a file over there with the data of this FGL 3-bus test system. You must remember that this data is provided using ohms per kilometer for the resistance and the reactance. And we create this video is also discussed and presented before. There is a YouTube video where we calculate the per unit values of these 3 bus bar test system. So if you want to watch the video, you can go here into the YouTube channel. There is a link here on the top right hand side. And also, if you want to access the MATLAB live script that we use in that video, what you need to go is follow this link directly to the GitHub repository and you will get that, okay? Well, it's time to implementing the FGL bus test system inside IPSA software, and it's very simple. There are 4 basic steps. First one is to create a graphical representation, the model network inside the software. That is basically a graph that is defining the connection and the different type of power system components inside the system. Then we will start to introduce the network data. That means voltages, powers, and so on. And then we will prepare the software for running the power flow calculation. One of the very interesting steps when you are using IPSA is that you need to define the slack bus bar. Finally, if you want, you can configure the outputs and the results that you will get in the single line diagram in the graphical object. And we will do that in 2 different ways. The first one is the numerical results, including the legends, the units, and so on. And finally, we will talk about the animations. Because one of the very interesting features of this software IPSA is that it's allow you to show in a very animated way, in very active way, the directions and the magnitude of the power flow. When I say power flow, it can be active power or it can be reactive power. So without further delay, let's go into the implementation of these 3 bus bar FGL test system inside IPSA. And what I will do is I will go into the DIgEnSysLab, Digital Energy System Lab, and there is a computer over there, a PC, with the IPSA already installed. And from there, you will be able to see, to watch every single step using the computer, using the software to create this test system. And without further delay, let's go there. So double click here at the icon and you can see that the software is starting up, and you can see this welcome window, and it's basically an information window that you can see welcome to the educational version of IPSA 2. And this software is not for commercial or consulting purposes. So what I will do now is close this welcome window by clicking here on OK, and that's all. As you can see right now, we are inside the software. We are inside the environment of IPSA. I will not go in details right now about the different part of the environment because that was covered in a previous video. What I will do now is I will start the creation of this FGL bus system. And the first step is to create the network. So we can do the following. We can go here to the top, say go into the menu file, and then we have here new and new network, okay? That is what I call the classic way to do the things, because you are using IPSA as a classical Microsoft Windows application, navigating inside the different menus and options, and you can create a new network. If you are a very advanced user, you can use the keyboard in your computer and you can press Ctrl key and N, and from there you can create the network. That is what we call the shortcut. But here on the top, you can see here in this bar, toolbar, you can see that on the left there is an icon that say new network. So that is probably the easier way to create a new network inside IPSA. So let's press over there, and automatically IPSA will start to collect information regarding the network that we are creating. In this case, the first dialog that you can see here in this window is related with selecting the type of diagram that you want to create inside the software. And as you can see, there are 4 different options in this IPSA version. You can see the first one, the default one, that is single line diagram, and that is the one that we are using today. This option is basically to create a network with a single line diagram or one line diagram depending on the side of the point that you are, but this is basically the option for today. However, you have the possibility of creating a graphic diagram with a map, especially if you are working in distribution networks and you want to show the specific location of every single asset. Probably you prefer to use the graphical diagram and the map. And also you have the possibility of creating a network without any single line diagram, just pure data, connectivity data, and later you can add your single line diagram, okay? Let me start here. We will select the first option, that is a single line diagram, and then we will press here this button at the very right hand side, that is next, okay, here. Now IPSA is requesting more information, and in this case is related to the single line diagram, and is requesting the title and the background. The title, I will use system 1 3 boss test system, and then you can select a background color. Here there are different options. You can select black or white depending on your interest. I will not do so. I just select the classical default background, but also IPSA allow you to include a background image, okay? I will not do so here, but I will press next. And from there, now IPSA is requesting the title, System 1, FGL 3 boss test system, and also is requesting information about the author. And I am completing here my name, Francisco Gonzalez-Longatt, okay? That is what I am doing right now. Regarding the system base, fortunately, this is the same base power that we have for the FGL 3 bus system, is 100 MVA. However, if you are creating another network, you can select here, define here the correct base that you are using. We are selecting here 50 Hz as default, and finally we press here finish. And right now, IPSA, the software, has created for you a graphical empty, I will say, an empty page that you can start to build your network. And now the process is very simple, because on the right-hand side, we have here symbols or icons for every single power system component. As you can see, they are already creating an order, and the only device that is activated at the very beginning is the horizontal bus bar, okay? What I will do now is I will put 3 of them in the location similar to the single line diagram that we have for the 3-bus system. And as you can see over here, IPSA is populating the database. You can see on the left-hand side, bus bar 1, 2, and 3. And also you can see now in black color, because now they are enabled all the icons for the different devices that we can find inside IPSA. Now what I will do is to install, for instance, a load a bus bar number 2, and that is very simple. The process is very simple. I select here the icon, then select here the bus bar, and for the direction, I click here, and this is going to the top. Okay, now we put the load over there, and the next step is to install generation units. There are different type of generation unit. We are using the simple one, the sine wave, and we are installing generators at bus bar number 1. Okay, let me go back here. We are installing generator at bus bar number 1 and also bus bar number 3. And we are already installed the generators. The next step is very simple because now we want to connect the transmission lines. And transmission lines, there are 2 terminals devices. What we need to do is select the first bus bar, then I click here in order to create a proper geometric representation. And finally here, click the final bus bar, and we finish with the bus bar number 1. Then we will do the transmission line 1 and 2. Then we will do the transmission line between bus bar number 1 and bus bar number 3, and job done. And finally, bus bar number 2 to bus bar number 3. Perfect. And right now we have completed the graphical representation of our 3-bus system here using IPSA. However, there is no data. We cannot run the load flow at this moment, the power flow at this moment. We need to complete the data for this analysis. Load flow is probably one of the simplest, so what we need to do is start to introduce the data for every single component, the network model, and we will start in the same way that we did before. Let's start with the bus bars, double click. I will change the name and I will call this the bus 1. And the rate voltage or nominal voltage, depending where you are, is basically 115 kV. Remember, this is an AC system, this is RMS values, and it's a 3-phase system. For that reason, this is a line-to-line voltage, okay? Let's go to bus bar number 2. Again, let me change the name, bus number 2, and now I will use 115 kV. Finally, the bus bar number 3, let me change the name, and this is bus number 3, and the nominal voltage is 150. Now we have finished with the bus bars, and now it's time to complete the data for this beautiful load at the top. Double click over there. Let me use a name, load 2. And if you go into the data that is provided for the FGL 3-bus test system, you must remember that the active power is 400 megawatts and the reactive power is 200. So right now you complete the data here for the load number 2. Now it's time for the transmission lines. Let me start with this one. This is the transmission line between bus bar 1 and 2. So let me use as name line, line 1, 2, sorry. And it's time to complete the resistance. In this case, we are using per unit values. Remember that in this case, IPSA is using per unit values, 0.02 the resistance and 0.04 the reactance. And for the length, we are using 1 kilometer. Okay? Now let's go to the transmission line between the bus bar number 1 and the bus bar number 3. Let me use again a fanatic name over here, line 1 and 3. Yeah, very original name. And now what we need to put is the resistance, 0.0, let me check the data here. Sorry, is 0.01. So let me include here 0.01 and the reactance is 0.03. Finally, the length, We are assuming 1 kilometer for this beautiful transmission line 1-3 and job done, okay? Finally, for the transmission line 2-3, again, we need to define the name, a very original name, line 2-3. And the resistance, if we go to the data provided, data is 0.0125, and the reactance in per unit value is 0.25. Finally, the length, the transmission line length is 1 kilometer. Perfect. We have completed the data for the different transmission lines, the load, and the bus bar. Now, what is missing here is completing the data of the generators. And to do so, let's start with the generator number 3. Double click. Let me use a very original name, Gen 3. And now what we need to define is what is the voltage, because remember the generator 3 is a PV generator, or a generator working at PV mode, active power constant and voltage constant, and the voltage is supposed to be controlled to stay in 1.04 per unit. And the active power output is 200 megawatts, and the maximum reactive power is 40 MVR, and minus 20 for the minimum reactive power. And we have completed the data for this generator number 3. Next step is the generator number 1. Again, a very original name, Gen 1. And in this case, this will be the slack bus bar. And for this slack bus bar, the voltage is defined, the control is defined for 1.05 per unit. So right now we have completed the data, the basic data that we require for a classical power flow. We are talking about the classical AC and positive sequence model load flow. What we need to do now is we need to define all the elements to fulfilling the power flow calculation, preparing for the load flow or power flow calculation. And the first step is we need to define the location of this amazing and very important slack bus bar. So IPSA, they decide to define the location of the slack bus bar in a very centralized way. And let me tell you, you can go here at the top, you can find the network menu, and there is an option over here, almost near to the bottom. You can see over there that they say slacks. Because IPSA is a commercial software, and many times in the industry, we need to define several slack bus bar. And I believe IPSA decided to centralize the location of all those possible slack bus bar in order to avoid the user be confused about the location of them. So the best way here is you press here this option slack, and right now you can see that there are 3 bus bar here at the voltage level of 115 kV. You can see bus bar number 1, 2, and 3. And in this FGL bus test system, we are selecting the bus number 1 as the slack bus bar, okay? The process is very simple. We select here on the left hand, we press this button in the middle, and we put now on the right hand side selected bus bar, the bus number 1 as the slack bus bar, okay? Well, we are near ready to run the first load flow, okay? To run the load flow or power flow, what we need to do is basically go here at the top. There is a tool bus bar, and you can see several options over there. And as you can see over there are several options like the classical load flow with no options, But also IPSA is enabled with the classical DC load flow. This is not a video about DC load flow, but DC load flow is very interesting and quite useful tool, especially when you are debugging problems related with reactive power in very large power networks, okay? So what I will do here is press the icon, and now we have the beautiful window related with the load flow properties. And as you can see at the top, the very two first options. You can see the convergency. In this case, the default value is 0.01, and we have 100 iterations. I will not put my hand over there. I don't suggest to do anything over there, because with those values, every single classical network must converge, and you will get the results of your load flow. What I select here is very important, is always run a flat start before a load flow. What does it mean? Well, basically what we are doing is, you must remember that the load flow solution is basically solving the nonlinear algebraic equations using iterative methods. And those iterative methods, they have an initial condition. They require an initial condition. It's a numerical initial condition. Basically is the value or the initial guess for the unknown variables. What IPSA is offering here is that you will start every single load flow calculation from the same initial condition. And the initial condition is called flat start. That means that we are starting from the same initial condition that is the rate values for every single unknown variable. So that's all. What we need to do now is we do OK, and you can see that automatically IPSA provide the numerical results of the load flow on the single line diagram. This is very useful, especially for my students. And as you can see over here, the results are represented, for instance, active and reactive power at the generators, active and reactive power in every single branch element. And finally, we have the boost voltage magnitude in per unit value for every single boost bar. However, time to time, we want to customize those results because we want to see more results. We want to get more details on the numerical solution. So IPSA is very simple to define styles, displays style and results. So it's very simple. You go here with your pointer, you go to any empty space, and you go to results and display styles, okay? As you can see over here, for instance, for the boost bar, we have the boost voltage magnitude in per unit as default, but we want to display the units and also displays the voltage angle. Then for the radial branches, we want to show the basically active and reactive power, but we want to show also the units. And let me select here 4 digital places. Let me go back and select 4 digital places. And finally, for the same in the branches, I want to see 4 decimal places and the units, okay? You can see over here, right now, IPSA is showing the 4 decimal places in all the quantities that I selected. Quite beautiful over here. You can see over here, this is 1.05, 0 degree. This is the slack boost bar. And also we get here the results of the generation, 200 megawatts and 40 MVR for generator number 3. Something that is quite interesting here is, as you can see, this is a branch element, and in this transmission line we have a resistance and reactance. So something that is quite interesting is that the sending power and receiving power, they are different because we have here some losses related with the series impedance of this transmission line. So one of the interesting features here on IPSA is that when we are representing load flow, what we are showing over here is, well, we can select the type of representation that we want if we want to see the results from front or two bus bar or the largest one of them, okay? I will not go in these details. I believe my colleagues on IPSA and TNA in Manchester, United Kingdom, I believe the documentation explained further than myself, okay? Something interesting here, because I know that my students probably they are puzzled about their results. If you go here to the generator number 3, you must remember that generator number 3 was working in a constant voltage mode. In a constant voltage mode, the synchronous generator, the generation unit, they try to keep constant the voltage, in this case to 1.04. However, if you look the results over here, you can see that the voltage is 1.0254 per unit. That is different to this voltage. And what is the reason for that? Well, if you remember the theory about load flow, you can see that this generator over here, there are some reactive power limits. And as you can see, the reactive power limits are between minus 20 MVR to 40 MVR. So this generator, synchronous generator, this generation unit is able to keep constant the voltage at 1.04 only, but only if this reactive power is inside this limit. However, you must remember that this bus bar voltage depends also or is related also with the power system. So in this case, the generator is trying to keep constant the voltage, but the voltage is going below because the machine cannot supply more reactive power. What I am trying to tell you is that in order to keep this voltage equal to 1.04, we require more reactive power. As the generator is limited to 40, this generator will keep constant this active power, and the generator changed the operational mode from PV, that means constant voltage, to PQ. And in this case, the voltage can drop. If you want to understand this, let me do a very simple simulation over here. Let me go here, and now I will put 1000 MVR and minus 1000 MVR. What I'm trying to do is virtually I am opening the capacity of this generator to produce more reactive power. And let me solve the load flow. When I solve the load flow over here, you can see that now the voltage is 1.04, but to do that, this synchronous machine requires to produce a reactive power of 112.43. That means in order to keep constant this voltage, this generator requires more reactive power. So coming back to the original data, 40 and minus 20, now you understand that this generator is trying to produce more reactive power, but because there is a real limit on the capacity of this generator to produce reactive power, reach the maximum 40 MVR, and now the voltage drop over here, okay? Well, this is a very interesting conclusion for my students and everyone watching this video. And the final part of this video, it will be something just for demonstration about one interesting feature, one more feature related to IPSA, okay? Let me right button over here. Let me go to results display styles. And what I will do is Right now, in the single line diagram, we are showing the active power or real power flow, but we want to do that in an animated fashion. So in the radial systems, we will show the animated real power, and let's do the following. Let's do the following also on the branches, okay? And now you can see over here, this is beautiful for my students and everyone watching in order to see how the active power is moving around. And what you can see over here is that 217 megawatts are coming from generator number 1. Generator number 2 is contributing with 200 megawatts. And you can see how the active power is divided through the transmission system. And through the transmission system, of course, the series impedance defines how the active power is moving around, specifically the resistance. But finally, we are receiving here, or 400 megawatts are reaching the load. So this is very interesting if you want to see how the active power is moving around. You can do the same with the reactive power. And also a very interesting feature that you can see is that the size of these dots, red dots, means the magnitude or the size of the active power moving through every single component. This feature is quite interesting. This feature allows the students to see how the power moves through the system. And that is very helpful, okay? Well, I believe that we are up with the time. We finished this video. We need to finish this video. I hope you enjoy watching this implementation of the FGL 3-bus test system using the software IPSA. And I would like to invite you to go to the IPSA website because you can start your, you can request a demo version of the software, and you have a period that you can use the software for testing and evaluating for your university or for your company. Well, that's all for this video today. Thank you very much for watching. If you like the video, please remember to put a like here in YouTube. Or also, if you like the video so much, please subscribe to the YouTube channel and you will get more information about new videos and new features. Thank you very much for watching. I will see you at the next one. Well, it's time to finish this video, and we already finished the implementation, the practical way to create a network model inside the software IPSA. And in this case, we implemented the classical 3-bus test system. And this video has been very, very interesting because we follow step by step the creation of the network, completing the data, configuring the power flow study, finally running the load flow, and we obtain over there some results. And the interesting feature about configuring the animated load flow has been presented over here. Well, this is the end of this video. I hope you enjoy. If you enjoy enough, please subscribe to the YouTube channel and also activate the bell in order that you receive notifications about the new videos. And also, if you want to make any question or if you want to put a comment, please feel free to drop the comment below. Thank you very much for watching this video, and I will see you at the next one. Bye.